Good morning to you. I'm Mr. Benjamin. I am your physics teacher for the moment. In this video, we shall be concentrating on the topic linear momentum. Have you heard of linear momentum before? If you haven't, I will tell you what linear momentum means in this video. And so let's look at what we'll be concentrating on in today's video. In today's video, we shall be concentrating on the concept of momentum and impulse, Newton's laws of motion, inertia, mass, and weights. Of course, we shall be concentrating on the following objectives. By the end of this lesson, you should be able to define linear momentum, state the equation, and explain the meaning of the terms therein. Define impulse, state the equation, and explain the meaning of the terms therein. State and explain Newton's laws of motion, and give relevant examples. And of course, you will be asked to do some simple calculations. In our SS1, under the topic fundamental and derived quantities, we highlighted or we listed linear momentum as a derived quantity and also a vector quantity, having both magnitude and direction. We shall be treating momentum quantitatively in today's video. So we have two types of momentum. We have angular momentum and linear momentum. But we will not be looking at angular momentum. We'll concentrate on linear momentum. Angular momentum will be taught at your A level. What do you mean by linear momentum? In physics, linear momentum is defined as the product of mass and velocity. Product of mass and velocity. P is equal to mass times velocity, measured in the SI unit of kilogram meter per second. Kilogram meter per second. Momentum explains two very, very important confusing concepts in physics: collision and explosion. And so we shall be looking at that on the superficial surface in today's video. We will not just concentrate on linear momentum, but we'll also look at impulse as we stated in our objectives. So what do you mean by impulse? Impulse simply means a sudden blow after an impact or during an impact. When two bodies come together, we say that is collision. And of course, there is an impact at that moment. And when two bodies fly apart after an impact, we say that is explosion. We define impulse I as force times time. Impulse is measured in the units of Newton second. Impulse is defined as force times time and is measured in the SI units of meter per second. Before we move further, let us take a look at this diagram that explains momentum and also impulse. Take a look at this. Consider these three pictures which shows an old airplane being slammed into a block of high density concrete at high speed. The first diagram here is talking about a collision. There is a collision here. And so this is a high density block, and then there is a strong impact here, a strong blow, and then there is an explosion here. So you can see that collision leads to a strong impact or a strong blow and then an explosion. Do you get that very well? And so we'll concentrate right now on Newton's three laws of motion. Newton's first law of motion states as follows. A body will continue in its state of rest or of uniform linear motion until acted upon by an external force. You see that? This calculator will remain here forever unless acted upon by an external force. The external force in this video is exerted using my fingers. I push it, it goes this way. And I pull it, it comes back this way. That is a simple explanation of Newton's first law of motion. What Newton's first law of motion is trying to say is that if there are balanced forces, there is a force that is keeping that body at rest. And we say that in physics, the state of inertia. The body is in its state of inertia, meaning the bigger the body, that is the mass. If the body has a bigger mass, the greater the inertia. Inertia is simply the tendency of a body to resist a force, but remain in its state of motionless. And so when the body is large, you have large inertia. The body has a greater tendency of staying one place forever. And when the body is small, it has small inertia. And so when there are balanced forces, the body will not move. For a body to move, the external force will have to overcome the force that is keeping the body at rest. That is the meaning of Newton's first law of motion. Newton's first law of motion fails to give or attach the SI unit or how to measure force, but only tells us what force can do. And so the second law of motion will be able to explain how this force can be measured. Newton's second law of motion states as follows. The rate of change of momentum is directly proportional to the impressed force. Let's take a look at this quickly. Newton's second law of motion states that if unbalanced or resultant force acts on an object, then the object will accelerate in the direction of the resultant force, and the acceleration will be directly proportional to the resultant force and inversely proportional to the mass of the body, of the object. Or the rate of change of momentum is directly proportional to the impressed force and takes place in the direction of the force. What Newton's second law of motion is trying to say is this: that force is directly proportional to change in momentum and inversely proportional to the time taken for the change. You see that? And so we have inversely proportional to mv minus mu all over t. That is Newton's second law of motion. That is what we have, as you can see on the board. Let's quickly take a look at what we have here. This is what you just see me writing on the board to save time. We have force is inversely proportional to the change in momentum over the time taken for the change. And then for change in momentum, this is given as this. This is mass times final velocity minus mass times initial velocity. Meaning the mass the mass of the body remains the same even during the change. And so we have this, we substitute this in the place of this, then we have this. And so we have this, we factor out m is here, so we factor out m. Then from your laws of motion, know that acceleration is velocity over time, and then we have this, and then we have this. And so to find the SI unit for force, we put k into 1, and so that gives us the SI unit of force as F is equal to ma, where F is a force in Newton and mass, m is the mass in kilogram, and then a acceleration in meter per second squared. Newton's second law of motion tried to give us the mathematical relationship that exists between impulse and momentum. So let's take a look at this quickly. This is what I'm trying to say. So from here, if you cross multiply, you get the mathematical expression for impulse and momentum. So take note, this equation explains the relationship between impulse and momentum. When you cross multiply, you have that relationship. Let's look at that quickly. We are saying that force is equals to mv minus mu all over t. If you cross multiply, this is what you have. You have mv minus mu is equals to force times t. And so this is change in momentum, and this is what? Impulse. So you can see that impulse is equals to change in momentum, where you have the SI unit here as kilogram meter per second, and then here you have the SI unit as what? Newton second. This is the expression that explains the mathematical relationship between impulse and momentum. Let's take a look at some examples that have to do with these equations. We'll look at example number 1. Example number 1 reads, a body of mass 5 kg with a velocity of 30 meters per second due is suddenly hit by another body and changes its velocity to 50 meters per second in the same direction. Calculate the magnitude of the impulse received. Solution and data, and of course a sketch. And so our data collection, we say solution. Our data collection. Our data collection will have our mass. Mass is equal to 5 kg, and our initial velocity u is 30 meters per second. Our final velocity v is 50 meters per second. And then we're asked to find the impulse. We're asked to find the impulse received. Let's quickly look at what we are discussing here. So you see this is our cardinal point. This is east, and this is west, and this is north, and this is what? South. And so the body is moving this way with an initial velocity of 30 meters per second. The body is this. And then another body comes from this way and hits it from this side. That body is unknown. It hits it on this side, and then the velocity increases to what? The velocity increases to what? 50 meters per second. And so we are asked to find the impulse, the blow. The body came here and hit it. So we're asked to find the impulse, the blow. So we're going to make use of this equation. We know that impulse I is what? Is mv minus mu. Sorry. Impulse I is force times t. And force is given as what? Force is given as what? mv minus mu all over t. Impulse is this, and force is this. So if you substitute this into this place, you have something like this. So we have our impulse is equals to mv minus mu all over t times t. So t will cancel t. Do you get that? And so we have our impulse is equals to mv minus mu. Mind you, our m remain the same. So our m is 5 times 50. 5 times 50 minus 5 times 30. 5 times 50, that is 250 thereabout. We have 250. And then minus 5 times 30, that should be 90. Let's verify that. 5 times 30. 5 times 30. Sorry, 5 times 30, that is 150. 150. And so, this minus this, you have 100 Newton second. And so, our impulse is 100 Newton second. Our impulse is 100 Newton second. I believe this example is very, very straight to the point. Let's look at example number 2. Example number 2 reads, a ball of mass 0.1 kg moving with a velocity of 30 meters per second is hit by a force which acts on it for 0.02 seconds. If the ball moves off in the opposite direction with a velocity of 25 meters per second, calculate the magnitude of the force. Very simple. So we will calculate that here using the same method as used above. Let's look at our data collection. We have our data, we have mass is equals to 0.1 kg. We have initial velocity u is equals to 20 meters per second. We have time taken t is equals to 0.02 second. We have final velocity is equals to 25 meters per second. And of course, the force is not given. The force is not given. This is the data we have on the board. The force is not given. How do we go about it? Very simple. First, we state the equation. We know that our force is equals to mv minus mu all over t. That's it. So let's move on. We substitute. So our force is equals to mass is 0.1 times 25 minus 0.1 times u times 20 all over the time taken. That is 0.02. 0.1 times this we have, I suppose we have 2.5. Well, 0.1 times 25, we have 2.5, very good. So 0.1 times 20, we have 2. So we have this minus 2 divided by 0.22. So we have this minus this, we have 0.5 divided by 0.02. So what do you have? So you have 0.5 divided by 0.02. Our final answer is 25 Newton. Therefore, the first equation is 25 Newton. Simple. And so I would like you to help me do this as your classwork. Just go through this question and try attempting this question. Newton's third law of motion. Newton's third law of motion states as follows. We don't have time, let's try and finish up. It states as follows. If a body A exerts a force on the body B must exert an unequal and opposite force on body A. That is, for every action there is an equal but opposite reaction. Force always acts in pairs. Newton's second law of motion is that law that is responsible for the launching of satellites in space. Let's quickly take a practical look at this law by looking at this diagram here. Take a look at this. There is a balloon with air, and the air is deflected. So if the air pushes the balloon down, then the air goes out, that is the gas, and then the balloon moves up. So this is the action. Action, air rush down, this is the action, and this is the reaction. The balloon will not move straight up, but will move randomly because the head is not sharp but blunt. That is what gives birth to the launching of the satellite in space, as you can see this rocket here. So this is the action, the gas burns down, this is the action, and then the rocket moves, or this is the what? Reaction. These are practical examples of Newton's laws of motion. We like to look at weight. Weight simply means mass times acceleration due to gravity, and that is mass times acceleration due to gravity will give you weight. And so at this point we would like to revisit our objectives from the beginning of this class. From the beginning of the class, we intended looking at the following objectives, and so we ask those questions here right now. I would like you to help me define linear momentum, state the equation, and also explain the meaning of the term bearing. Define impulse, state the equation, and also explain the meaning of the term bearing. State and also explain Newton's laws of motion and give relevant examples. And of course, help me do this work you see here, that determine the impulse experienced by these moving objects. In summary, we said momentum is defined as the product of mass and velocity. It is measured in the SI units of kilogram meter per second. Impulse is defined as what? Force times time. Impulse is a blow during an impact. And so impulse and momentum are related in Newton's second law of motion. So we state Newton's first law of motion as a body will continue in the state of rest or uniform linear motion until acted upon by an external force. Meaning, when there are balanced forces, the object cannot move. For an object to move, the external force will have to overcome the resisting force. And so we state Newton's second law of motion as the rate of change of momentum is directly proportional to the impressed force and inversely proportional to the time taken for the force to act. That gives birth to the famous law of motion, the famous equation of motion: force is equal to mass times acceleration. And so we also have force equals to change in momentum all over time. Force equals to change in momentum over time is that equation that gives the mathematical relationship between momentum and also impulse. And so we look at inertia as a tendency of an object to remain in a state of uniform rest and also resist force. The bigger the object, the bigger the inertia. That is, the massive the object, the more the inertia. And then the smaller the object, the smaller the inertia. And when the object is big, you need a large amount of force to push it from its point of rest to a given position to a particular direction. Thank you for watching this video. When next we meet, we shall be looking at the law of conservation of linear momentum. Thank you and God bless you.